All right, so I'm going to try and do a screencast of this problem that I messed up in class a couple of weeks ago, where I gave you an acceleration versus time graph. That's the one that's in blue right here. And asked you to first find the velocity versus time graph that matches it, and then to find the position versus time graph that matches that. And we did the velocity versus time fine, but then I got confused when I was thinking about the limits of the integration and exactly how that related to the problem as I was trying to work out the position functions. So I promised that I would try and fix that. Okay, so to fix that, I'm going to try and do this whole derivation of this problem. And we've got a couple different time frames in here. We've got time 0 to 2 seconds. We've got time 2 to 7 seconds. And we've got time 7 to 10 seconds. 7 to 10. Those are the time frames that we're talking about. And we've got a different acceleration in each one of those, a different constant acceleration. The A is 2 in the first bit. It's -1 in the second part, and it's +4 in the third. And we're going to figure out velocities and position functions that go along with all that data. So I'm going to fill in these answers as I get them over here. So the starting velocity at time 0 here was 0, and the starting position at time 0 is also 0. So I know that the acceleration is 2, and I know that the velocity is the integral of that acceleration. And I talked in class about how in many ways it's better just to go straight to the solved kinematic equations that are the result of doing these integrals. But because there's been so much confusion about it, I thought it would be a good idea to just do this in integral form and help us reason through what all of that means. So when I say this, really what I'm saying is that the change in the velocity is this integral. That's how much the velocity changes, because I really need to know something about what it started at in order to be able to get a full function out of that. So the velocity is the integral of 2 dt. That means the velocity is 2t plus a constant. Okay, so I'm wanting that to be a general velocity function where I can plug in any moment in time and it will tell me what the velocity is going to be. But in order to do that, I need to know what that c is. So I plug in velocity at time 0 equals 0. That was my starting boundary condition for the velocity, equals 2 times 0 plus c. So I'm plugging in time 0. The velocity at time 0 is 0. That tells me that the c must be 0. Okay, that means the velocity function that I wanted was velocity at time t equals 2t. Simple. Okay, now I want to do the position function. So x, the position function is the integral of v dt. That's the integral of 2t dt. That's t squared plus a constant. Okay, well, to figure out what that constant is, I need to plug in a boundary condition. The boundary condition is that at time 0, the position started at 0. So x of 0 equals 0 equals 0 squared plus c. That must mean that that c is also 0. Okay, so the position function for those first 2 seconds is t squared. X of t equals t squared. There we go. So I figured out exactly what the velocity function is and what the position function is for those 2 seconds, but this only applies for those 2 seconds. Okay, so now I'm moving on to the time frame 2 to 7 seconds. That's the middle part of it. And I know the acceleration is -1, and I know this stuff about what was happening during those previous 2 seconds. So just like I needed to know over here, I need to know what the starting velocity and starting position was, I also need to know the starting velocity and the starting position here for those for this 5-second time frame. I'm going to get that starting velocity and starting position from the functions that applied for the first 2 seconds. So I'm taking the end of this piecewise function and saying, okay, the velocity at 2 seconds is 2 times 2, which is 4. So the end point I want is velocity at time 2 equals 4 meters per second. So I'm getting that from this. And then I want to do the same thing for the position. The position at time 2 is 2 squared. That's also 4. So I'm getting that one from there by plugging in the time that is the endpoint of that domain. Okay, so then I'm going to set up these same integrals that I did before. I'm going to integrate the acceleration, figure out a velocity function, and I'm going to integrate that velocity function to get the position function, and I'm going to figure out the c's that match it. All right, so velocity is the integral of a dt, and the a is -1. So that means that the velocity is the integral of -1 dt. That means the velocity is -t plus a constant. How do I figure out what the constant is? I plug in an endpoint for this piecewise piece of the function. V of 2 equals 4 equals -2 plus c. That means the c must have been 6. So the velocity function I actually wanted is v of t equals 6 minus t. 6 minus t. All right, now I'm going to set up this integral of the velocity function to get the position function. So x equals the integral of 6 minus t dt. That is equal to 6t minus t squared over 2 plus a constant. How do I figure out what that constant is? I look at the endpoint of my domain. The position at time 2 is 4. So that means x of 2 equals 4 equals 6 times 2 minus 2 squared over 2 plus a constant. Then I simplify that. 4 equals 12 minus 2 plus a constant. That means the constant is -6. So then the position function that matches this part of the domain is x of t equals -6 plus 6t minus t squared over 2. -6 plus 6t minus t squared over 2. So I've got a portion of this problem that's about the time 2 to 7 seconds. This over here is about 0 to 2. I got my starting points for this 2 to 7 seconds from the endpoints of that domain. And I'm going to do the same thing again for the 7 to 10 seconds time. Okay, I'm going to move this over to give myself a little bit more room to work. So 7 to 10 seconds, the a is plus 4. Okay, so then I need to know, just like before, I need to know a starting velocity and a starting position at time 7. So to get that, I'm going to have to plug those times into these velocity functions for the previous time domain. So the velocity at time 7 was 6 minus 7 is -1. So v of 7 equals -1. Then I've got position at time 7, x of 7 equals, I worked this out on another whiteboard. So to save space, I'm going to give the result. That's 11.5. So I got those two things just like before by plugging in into those two functions. So I got that 11.5 by plugging 7 into here and saying -6 plus 42 minus 49 over 2 gives 11.5. Okay, now I'm going to use that to figure out the functions that go with it. So the velocity is the integral of a dt, and the a is 4. So it's the integral of 4 dt. So the velocity is 4t plus a constant. That means So the velocity at time 7 is -1. That equals 4 times 7 plus a constant. That's -1 equals 28 plus c. That means the c must have been -29. So velocity as a function of time is -29 plus 4t. We're almost there. I got to get the position function that goes with this. So I have to do x equals the integral of -29 plus 4t dt. That's -29t plus t squared, sorry, 2t squared plus a constant. And I plug in my starting point, x of 7 equals 11.5. So x of 7 equals 11.5 equals -29 times 7 plus 2 times 49 plus a constant. You rearrange all that, and then the c ends up being, let's see, I ran out of space there. The c ends up being 116.5. So that gives you x of t equals let's see, 116.5 minus 29t plus 2t squared. There we go. That is the whole thing. And the thing that I messed up in the previous version of it was in not thinking consistently about how to deal with these endpoints and what that meant about the function. So it's really important that these results for these functions, it's a piecewise. This velocity function only applies for 7 to 10 seconds. That position function only applies for 7 to 10 seconds because the acceleration changed. Same thing here, between 2 and 7 seconds, this velocity position function only applies for that domain. This velocity position function only applies for that domain. So you can put all of those into your graph over here, and this is what that looks like. You've got the position function in several pieces, you've got the velocity function in pieces, and you've got the acceleration function in pieces. And this is what those equations look like. And you can see that we've restricted the domain so that it's only showing it for those 2 seconds. This part is only showing it for the 5 seconds, and this part is only for those last 3 seconds. And you can see the parabolas. There's a parabola for this, there's a parabola for that one, and there's a parabola for that one with the right kind of quadratic term to get the right acceleration, and the right sign to have it pointing the right direction so that it's curved up, curved down, and so on. So just to conclude, this problem is about as ugly as anything I want us to do. There's several different pieces. You've got to think carefully about the endpoints. But in essence, what you're doing all the way through is you're saying, I've got an acceleration, I have a starting velocity and a starting position, do some stuff with the integrals or the areas or the amount that things change to figure out what the new functions for the velocity and the position are, and then keep repeating that as you move forward in time.